Hello students, welcome to Solve classes. And question here again is the pair of compounds in which both members show LMCT band in their electronic spectra. LMCT means ligand metal charge transfer. Okay, condition for ligand metal charge transfer is what? That the metal should be in the higher oxidation state. Okay, or it can be happening in a tetrahedral complex. Okay, whereas there is a PD mixing. Okay. Now, if you look at the first option over here, this can be having charge transfer. Okay. If you want to have a reference, then the book I would mention is Housecraft. You can go and have a look at it. This particular, so this question is directly from Housecraft, as you can say. This is going to have metal to ligand transfer. Why? When we have bipyridine and the metal is in low oxidation state, then obviously it is going to be metal to ligand charge transfer. That is the thing that you have to remember. As I said, if FeCl4 can give you charge transfer, this is also tetrahedral, so DB mixing can occur, so there should be a charge transfer here. This is in 7 oxidation state. Oxygen is here, it is oxide. So here from oxide to technetium, we can have a ligand to metal charge transfer. So both of these complexes are going to show ligand to metal charge transfer, and that should be our answer. But why these two are not? Let's have a look. Rhenium +7, oxygen. Similarly, for as we have seen in technetium, this also can show LMCT, but ruthenium bipyridine, just like Fe bipyridine, will be having metal to ligand charge transfer. So one is showing and one is not showing. Iron phenolphthalein, just like bipyridine, again it is going to be metal to ligand charge transfer complex, whereas FeCl4, as I explained before, will be showing ligand to metal charge transfer complex. Okay. So answer here should be 2. Next. All right, this is an interesting question. During the binding of O2 to myoglobin, consider the heme in XY plane. The molecular orbital of O2 and the atomic orbital of Fe involved in the formation of the sigma bond is, we have to find out the orbitals involved here. Okay, again a question that is straight away from Atkins. Okay, the 5th edition you can consult. You will find this picture where you have a histidine that is called distal histidine. Okay, this is the heme that is lifted a little bit, continue to the imidazole. When it is combined with oxygen, it will be in the bend fashion. Okay, so that is how it happens. Now, before going to this section where the direct answer is there, I'm going to consider the molecular orbital picture of the complex over here. Let's see. Now see, this is a square pyramidal geometry. For a square pyramidal geometry for iron, which is in state 2 and high spin, how should be the arrangement of orbitals? Square pyramidal geometry. Okay, that means the Z components will be of lower energy. So from octahedral field, you can think of splitting of the orbitals of the T2G and EG set, and we will have this dxz and dyz lower in energy. Then we have dxy, then dz square and dx square y square. Okay. And what will happen over here? You have to put 6 electrons because this is a D6 system. All right. Now for oxygen, we have to consider the highest occupied molecular orbital, which is what? Pi star. All right. Now when oxygen is acting as a ligand to the hemoglobin, what is happening, or myoglobin, this particular spin pairing will occur. Okay, so we can think this electron is going here, this particular pi star becomes empty. So from a triplet it becomes singlet. That is why you see it is being mentioned over here. The model considers the O2 ligand to be a singlet state, in which the full 2 pi G orbital donates an electron pair. Okay, and other 2 pi G orbital acts as a p electron pair acceptor. Okay, so this is going here, this becomes empty and this becomes the lone pair of electron. Okay, so now these two can combine with this set of orbitals from the iron, and we will have this set of molecular orbitals where we can now consider, while this combination has taken place, okay, these electrons are going to be filled over here, again using above principle and the Pauli's exclusion principle. And so this is the MO picture. So what is happening over here now? This electron is coming from the oxygen in the Z direction. Now, which is the orbital that will be lying in the Z direction? For a square pyramidal geometry, obviously it is going to be dz square. So it is the Fe dz square that will accept the lone pair from the oxygen 2 pi g. Okay. Now, while giving away the electron density back to the oxygen, again it will be the pi star orbital that will be functioning as the acceptor. Okay. And now, since it has been said that this is the xy plane, so if this is the xy plane, obviously the orbitals lying in this direction for a suitable combination with the oxygen 2 pi g will always be 3d xz, 3d xz. So obviously the orbitals that are going to be involved, okay, in the sigma bonding, and over here they have not asked for the back bonding, but for the sigma bonding, we can say it is going to be pi star and dz square. Okay, so I hope that explains the query that you had in this question. The next question we're going to take. All right. Okay. Now here it is being said the rate of substitution of chloride by pyridine in ethanol in the following complexes is. Well, this question is again from Hui. Okay. It does talk about the reaction ratio rates, okay, reaction rate ratios of PT, PD, and Ni, as I'm highlighting over here, you can see, are approximately 1, 10 to the power 5, 10 to the power 7. That means very fast for nickel, less for palladium, and very slow for palladium. What could be the reason for this? Okay, even in the Hui, there is a question regarding this, okay, in the question section. What is the rate of reaction for nickel and platinum complexes? Okay, so obviously our answer should be over here. Looking at this data is going to be 1, 2, 3. Now, most of the square planar complexes, this is the explanation. Okay, they undergo the associative mechanism. Okay, that means they want to form, the ligand will come, they will form a square pyramidal, not a square pyramidal, rather a TBP intermediate, okay, or go through a TBP transition state. So if it is following associative mechanisms, obviously there should be an intermediate, which will be TBP. Now please understand, nickel is smaller in size, palladium is little bigger in size, and platinum is larger in size. So larger the metal, better will be the coordination number. Okay, it will allow higher coordination number. So we can say for nickel, the intermediate, which is TBP, will be less stable. Okay, it will be sterically hindered. So obviously, if it is following associative pathway, and in such a pathway, if the dissociation of the Cl is the rate determining step, okay, we can think that nickel, around nickel, the groups are more strained. Because there is more strain or repulsion, Cl will run away faster, okay, or cleave away faster. Then we can when we consider the platinum. So what is the reason again? Nickel is smaller in size, so around it, the trigonal pyramidal geometries will be strained more, but platinum being larger in size, trigonal pyramidal geometry will be more suitable. So here some strain is occurring, that is why the Cl will cleave away faster. Here less strain is occurring, so Cl will not cleave away faster. So this will be slow rate and this will be fast rate. I hope that explains all the inorganic questions that we had. Next, we'll be discussing the organic part. Keep visiting Sarasa classes, and thank you for listening. Have a great day.